The night sky often seems still, as if the stars have been pinned in place above a sleeping world. Yet nothing in the universe is truly motionless. Planets turn in darkness. Stars roll through their long lives. Dead suns spin with the patience of hidden clocks. Farther out, galaxies carry billions of stars through slow rivers of gravity, while, in the deepest places, black holes twist the space around them until light itself begins to bend into rings. Rotation is one of the oldest memories in the cosmos, left behind by collapsing clouds, dying stars, drifting plasma, and the quiet pull of matter gathering toward matter. This is built for rest, for a slow passage through the turning universe without urgency, without noise, and without the need to hold every detail in mind. The journey moves from the dark edge of black holes to the red surface of Betelgeuse, to neutron stars sending patient signals across the Milky Way, to the wide spiral arms of galaxies, and finally back to Earth, where liquid metal deep below the ground helps shape the magnetic shelter around life. Each motion leaves a trace. Each trace becomes a way to listen. And as the story unfolds, the cosmos becomes less like a machine rushing forward and more like a vast, dark ocean, turning quietly in its sleep. The night above a quiet planet can look almost motionless. Stars hold their places in the dark. The Milky Way lies across the sky like a long mist of frozen light. A moon, if there is one, seems to hang without effort, its face turned toward the ground in the same calm way it has shown for ages. Beneath that sky, mountains sit in darkness. Oceans breathe against their shores, forests settle into shadow, and the world appears briefly still. That stillness is only a surface. The planet is turning. The ground is carrying every sleeping city eastward through space, not with the noise of machinery, but with the silence of a body too large to announce its motion. Every stone, every river, every rooftop, every animal curled in the dark is being carried along by that rotation. The air turns with it, the clouds turn with it. The sea, though it folds and shifts under winds and tides, belongs to that greater motion too. Nothing needs to feel fast for motion to be real. A world can move with immense speed and still seem peaceful from the inside. Far above the atmosphere, the same turning becomes easier to imagine. The planet shows itself as a sphere, blue and white, with dawn sliding over one edge and night closing over the other. Clouds draw slow spirals over ocean basins. Storms rotate in wide arms. The polar ice catches sunlight, then loses it again. In that view, day and night are not events that arrive from nowhere. They are the visible edge of a turning world, one half leaning into the star, the other half resting in its own shadow. Rotation is older than the planet itself. Long before Earth has oceans or continents, dust and gas move through a young solar nebula, drifting in a broad, flattened cloud around the newborn Sunday. Tiny grains touch and cling, pebbles gather into stones, stones become larger bodies, and each small collision leaves behind a little motion, a little tilt, a little memory of direction. There is no perfect stillness in that beginning. Every piece arrives from somewhere. Every impact gives something to the growing world. Slowly, over millions of years, the young Earth becomes not only round, not only hot, not only heavy, but turning. The same pattern works in quieter places, far from any planet. A cloud of cold gas in deep space may appear loose and shapeless, spread so thin that it hardly seems like matter at all. Yet the cloud is never perfectly at rest. One region drifts a little faster. Another carries a faint sideways motion. Gravity draws the cloud inward, and as the material contracts, that small original motion becomes harder to ignore. The cloud spins more clearly. A flat disk forms around a brightening center. Out of the disk, stars and planets may take shape. In this way, spin becomes a kind of memory. It remembers the direction of a collapse. It remembers the touch of passing bodies. It remembers the angle of a collision that happened before any surface existed to record it. A planet turning in the dark is not simply moving through the present. It is still carrying traces of the events that made it. The sun turns too, though not like a solid stone. Its surface is made of plasma, a gas so hot that electrons have been stripped from atoms, leaving charged particles flowing through magnetic fields. Near the solar equator, the surface completes a rotation more quickly than the regions closer to the poles. Different latitudes slide at different rates, and the magnetic field is pulled and twisted by those unequal motions. Over time, loops of magnetism rise through the bright surface. Sunspots appear as darker islands. Arcs of charged material lift and fall back. The star is not a lamp fixed in space. It is a restless body, slowly churning, slowly turning, holding its own weather in fire. Beyond the sun, the planets keep their separate rhythms. Some rotate quickly, with short days and flattened shapes. Some turn slowly, as if resisting the clockwork around them. Venus turns in a direction opposite to most of its neighbors, its thick clouds hiding a surface where the sun would rise from an unfamiliar side. Uranus rolls almost on its side, its seasons stretched into long extremes of light and darkness. Each world carries a different history in the way it turns. A tilt may speak of an ancient impact. A slow rotation may speak of tides. A strange direction may speak of a past that cannot be seen directly, only inferred from the motion left behind. The pattern extends outward, past the scattered ice of distant belts, into the wider night of the Milky Way. Stars do not simply sit in the galaxy like lights on a ceiling. They orbit the galactic center in broad paths, carried by gravity through a disk of gas, dust, and dark matter. The sun itself is moving around that center, following a path so large that a single circuit takes hundreds of millions of years. During one such orbit, continents can split, seas can open, forests can rise, animals can appear and vanish. A star's path is so wide that life may change completely before the turn is complete. This kind of motion is almost beyond ordinary sensation. It is too large to hear, too slow to watch in a single lifetime, too steady to feel beneath the skin. Yet it is present everywhere. The night sky does not need to streak or blur to be moving. Stillness, at cosmic scale, is often only motion seen from too close or over too short a time. In the deepest objects, rotation becomes stranger. A dying star can collapse until its core becomes a neutron star, a sphere only the size of a city but heavier than the Sunday. As it shrinks, its spin grows faster, the way a skater turns more quickly when drawing in the arms. Magnetic fields tighten. Beams of radiation sweep through space. Somewhere far away, a telescope may receive the signal as a pulse, then another, each one arriving with patient regularity from a body that is no longer a normal star. Farther still, around black holes, rotation changes the shape of the surrounding space. The darkness at the center may not move in any familiar visible way, yet its spin can drag nearby space-time into a slow whirl. Light bends, matter circles. The boundary between motion and geometry becomes soft. What turns there is not merely gas or dust, but the stage on which gas and dust are moving. The universe is full of these hidden rotations. Some are gentle enough to make days and seasons. Some are violent enough to twist magnetic fields until they release storms of radiation. Some are so broad that galaxies carry whole generations of stars through spiral paths. Some are buried beneath the ground, where liquid metal inside Earth circulates and helps maintain a magnetic shelter around the living surface. Under a quiet sky, all of it continues. The planet turns, the star turns, the galaxy turns. Far away, collapsed suns keep their clocks. Red giants breathe across their swollen surfaces, and black holes draw space into dark, circular motion. The apparent stillness of the night is not empty. It is filled with turning, with old momentum, with the slow memory of matter finding its path through darkness. A quiet law follows matter through space. It does not speak in flashes or sudden commands. It works through distance, mass, and motion, leaving its mark in the slow turning of worlds and in the quick spin of collapsed stars. A body that begins with even the faintest sideways drift does not simply fall inward in a straight line. Gravity draws it closer, Yet the old sideways motion remains, and as the path tightens, the turning becomes stronger. The law is called conservation of angular momentum. The name is formal, but the image is simple. A wide movement becomes a faster movement when the same motion is held closer to the center. A skater on ice can show it with the body alone, turning slowly with arms spread outward, then spinning more quickly as the arms draw in. Nothing new has been added. No hidden motor has started. The motion has only been gathered into a smaller space. In the universe, the same idea is written on a much larger scale. A cold cloud of hydrogen and helium may hang across several light-years, thin enough that each particle has wide darkness around it. The cloud is not still. No natural cloud ever is. A passing star may have tugged one side. A nearby supernova may have pressed against another. A ripple of gravity may have moved through the gas long before the cloud begins to shrink. These small motions do not vanish when gravity takes over. They remain inside the collapse, like faint lines in water that keep their direction after the pond grows dark. As the cloud contracts, the material near the edge cannot simply drop into the center. It carries sideways motion, and that motion makes it orbit. The falling cloud flattens into a disk, not because it has chosen a shape, but because motion allows matter to fall more easily in some directions than in others. Gas moves inward along the disk. Dust grains collide, cling, and break apart. Some clumps survive. Others are ground down and return to the flow. Near the center, pressure and heat rise until a star begins to burn. Around that young star, the remaining disk keeps turning. The disk is not smooth. It is filled with small eddies, clumps, shadows, and bright regions warmed by the infant star at the center. Dust settles toward the middle plane. Ice forms farther out, where the light is weaker. Pebbles drift. Larger bodies grow by collision, then disturb the smaller material around them. A planet forming in such a disk does not need to be given spin from outside. It inherits motion from every strike, every merger, every uneven flow of material falling onto its surface. Some worlds are born with fast days, others slow over time. Tides can pull against rotation, drawing energy out of a planet and giving it to an orbit. The moon is doing this to Earth, very gently. Each ocean tide raised by lunar gravity sits a little ahead of the moon because Earth is turning beneath it. That offset tugs back. The planet's rotation slows by a tiny amount, and the moon drifts farther away. The change is small in a human year. Over deep time, small changes become landscapes of motion. The moon itself has already given up most of its spin. It turns once for every orbit around Earth, keeping the same face toward the planet. This is not because one side is fixed by magic, or because the far side is somehow forbidden. It is the result of tides working patiently on stone, pulling, flexing, warming, and slowing the body until rotation and orbit settle into a shared rhythm. Many moons across the solar system live in this quiet lock, turning in step with the worlds they circle. Rotation can also be changed by violence. A young planet may be struck by another body and left tilted, scarred, or spinning in a new direction. Uranus carries such a memory in its sideways posture, rolling around the sun with its axis lying close to the plane of its orbit. Venus turns slowly and backward, compared with most planets, a motion that may preserve the trace of ancient tides, impacts, atmospheric drag, or some mixture still not fully settled. The past cannot be watched again, but the turning remains. It is a fossil made of motion rather than stone. Even smaller bodies hold these records. Asteroids tumble. Comets rotate as sunlight warms their ice, releasing jets of gas that act like faint thrusters. Some asteroids spin so quickly that loose material slides away from the equator and drifts into space. Others rotate in slow, uneven patterns, their shapes and histories written into awkward motion. A small rock moving between planets may look simple from a distance, but its spin can reveal collisions, fractures, internal hollows, and the soft gathering of rubble under weak gravity. On a star, the law becomes more fluid. A star is not solid, so one part may turn at a different rate from another. In the Sun, the equator rotates faster than the higher latitudes, and the plasma carries magnetic field lines with it. These lines stretch, twist, and rise through the surface. Dark sunspots gather where magnetic knots suppress the upward flow of heat. Loops of glowing gas lift into the corona and fall back again. The Sun's rotation is therefore not only a mechanical motion, it is a way of winding magnetic energy into form. The same winding appears in young stars, where magnetic fields connect a star to its surrounding disk. Material follows those fields inward. Jets may shoot outward along the poles, narrow and bright against the dark cloud that gave birth to the system. Rotation feeds both the disk and the jet, shaping a young star's first visible gestures. Matter falls in, matter escapes. The two motions belong together, balanced around an axis that began as a faint drift inside a cloud. There is calm in this law because it does not rush. It only preserves what matter already carries. A forming star keeps the memory of its cloud. A planet keeps the memory of impacts and tides. A moon keeps the memory of being slowed by its companion. A galaxy keeps the memory of the larger flows that assembled it. Even when the scale becomes too large to picture easily, the principle remains steady. Motion can be moved inward or outward. It can be shared, drained, twisted, or locked. It is rarely erased. This is why rotation appears almost everywhere in the cosmos. Not because everything is built like a wheel, and not because everybody has the same history, but because perfect stillness is rare. A little sideways motion is enough. Given gravity and time, that small beginning can become a planet's day, a star's magnetic weather, a moon's locked face, or a disk of gas feeding a newborn sun. The quiet law of spin gives the universe a hidden rhythm. It sets no audible beat, yet it is present in the changing length of a day, in the swirl of a storm, in the tilt of a planet, in the slow drift of a moon, and in the luminous rings around young stars. It gathers the past into motion and carries that past forward without words. Long after the first cloud has disappeared, long after the impacts have cooled, the turning remains, patient and nearly silent, moving through the dark. Far from the familiar light of ordinary stars, there are places where gravity gathers so deeply that space seems to lose its easy shape. A black hole does not need to announce itself with a surface, a color, or a flame. It may sit at the center of an invisible silence, known only by the way nearby matter moves, by the way light bends, by the way stars trace strange paths around something that cannot be seen directly. The darkness is not an object in the usual sense. A planet has a surface. A star has a shining outer layer. Even a cloud of gas has edges that can be softened by light. A black hole presents something different, a boundary drawn not by stone or plasma, but by escape. Outside that boundary, light may still find a path away. Inside it, every future path turns inward. The line between those two conditions is called the event horizon. The event horizon is often pictured as a dark sphere, clean and absolute, hanging against the star field. That picture is useful, but it can also mislead. The horizon is not a wall. It is not a shell of material waiting to be struck. A traveler crossing it, in the simplest description, would not feel a sudden surface against the body. Locally, space may seem ordinary for a brief time, especially around a very large black hole where tidal forces at the horizon can be gentle. The change is deeper than touch. It belongs to the possible directions of the future. Outside the horizon, a rocket with enough power can still turn away. A beam of light can still move outward, though its path may be badly bent. A falling stone may still be thrown back if the force is great enough. Inside the horizon, the word outward loses its old meaning. Every direction that once might have led away now leans toward the center. The black hole is not merely pulling hard. It is shaping the map of possible motion until escape is no longer one of the routes. This is why light gives the black hole its name. Light is the fastest signal in the universe, the measure that ordinary matter cannot outrun. If even light cannot climb away from within the horizon, then no message, no image, no reflection can come back from that region. The inside is hidden, not because telescopes are weak, but because the geometry of space-time allows no returning path. Yet, black holes are not completely unknowable. Their surroundings speak for them. A star moving near a hidden mass may swing around it in a long, stretched orbit. Gas may fall inward and heat until it glows in X-rays. Dust may gather into a disk, circling faster as it approaches the center. Light from background stars may bend around the black hole and arrive from altered directions, as if the invisible object has placed a lens into the sky. In these outer signs, the hidden body leaves a readable trace. The simplest description gives a black hole only a few outside properties. It has mass. It may have spin. It may carry electric charge, though natural black holes are expected to be nearly neutral because surrounding matter tends to balance charge quickly. For the quiet path of this story, mass and spin matter most. Mass tells space how strongly to curve. Spin tells nearby space how deeply it is being dragged into motion. Mass is the first clue. If a great amount of matter is squeezed into a small enough region, the escape speed from that region rises. Around Earth, a rocket can leave if it moves fast enough. Around a more massive body, escape demands more energy. Around a black hole, at the horizon, the needed escape speed becomes the speed of light. The boundary marks the place where even the fastest possible motion is no longer enough to return to the wider universe. This does not mean that a black hole is a cosmic vacuum cleaner reaching across space without limit. Far away, its gravity behaves like the gravity of any other object with the same mass. If the Sun could somehow be replaced by a black hole of equal mass, Earth would not immediately fall inward. The planet would continue to orbit that mass from the same distance, though light and warmth would vanish. The danger of a black hole belongs to closeness, to the region where curvature becomes severe and paths begin to close. Nearer to the horizon, the sky would no longer look simple. Light that passes close to the black hole bends around it. Some rays that would have traveled straight are redirected. Others loop part way before escaping. The result is a warped view of the universe, with stars displaced, duplicated, stretched into arcs, or gathered into thin rings. The black hole itself remains dark, but the space around it may glow with distorted images of everything behind it. When gas is present, the scene becomes brighter. Matter falling toward a black hole often forms an accretion disk, a flattened river of plasma orbiting at high speed. Friction, compression, and magnetic turbulence heat the gas until it shines fiercely. The black hole does not shine from its own surface, because there is no surface to glow. The light comes from the material outside, from matter losing energy as it spirals inward. At the center of the mathematical description lies the singularity, though that word is more a warning than a completed picture. General relativity points toward a place where density and curvature become infinite. Current physics begins to fail there. A true understanding would need gravity and quantum theory to work together in a way that has not yet been fully achieved. The singularity may not be a real point in nature as the equations suggest. It may be a sign that the known description has reached its edge. For a non-rotating black hole, the central idea is drawn as a point. For a rotating one, the mathematics changes. The hidden center is often described as a ring, and the space around it carries the influence of spin. This distinction matters because the universe rarely makes perfectly still objects. Stars rotate. Gas clouds rotate. Collapsing cores inherit motion from the bodies that came before them. When such a core becomes a black hole, its spin does not simply disappear. It becomes part of the shape of the surrounding space. The dark edge of a black hole is therefore not only a border of no return, it is a place where several meanings of motion meet. Matter falls, light bends, time stretches differently for observers far away and those close to the horizon. Space itself begins to lose the plane geometry of ordinary distance. A black hole is quiet in the sense that no voice comes from within it, yet the region outside may be full of motion, heat, and curved light. From a distance, it may appear as a round absence against a brighter background. Closer in, that absence becomes a lesson in the shape of reality. The event horizon does not mark a solid surface, but the last open edge of escape. Around it, the universe is still visible, still moving, still leaving signs in light. Beyond it, the signs end. The story must continue outside, in the glow, in the bending star field, and in the turning space that surrounds the dark. A rotating black hole does more than sit inside space. It changes the motion of the space around it. The idea is difficult because ordinary experience separates the stage from the actors. A stone moves through air, a boat moves through water, a planet moves through the dark. Space itself seems like the quiet background that allows motion to happen, not something that can be pulled into motion of its own. Near a spinning black hole, that separation begins to soften. The black hole carries angular momentum, and general relativity says that mass and energy do not merely occupy space-time, they shape it. When a massive body rotates, the geometry around it is dragged along in the direction of that rotation. The effect is known as frame dragging, a name that sounds technical but points toward a simple image. The local frame of reference, the set of paths that nearby objects naturally follow, is being carried around the black hole like water drawn into a broad, dark whirl. This does not mean that space becomes a material fluid. It is not water, not air, not a substance that can be touched. Yet the paths through it behave as if the turning mass has leaned the whole region sideways. A body trying to hover near a spinning black hole cannot pretend that the surrounding geometry is still. The closer it moves, the more strongly the allowed paths are tilted in the direction of spin. Frame dragging is not only a black hole effect. Earth produces a very small version of it. The planet's rotation gently twists the space-time around it, too weak to be felt by the body or seen with the eyes, but strong enough for careful instruments to measure. Around a black hole, the same effect is deepened by extreme mass and compactness. What is delicate around Earth becomes dominant near the horizon. The region where this turning becomes impossible to resist is called the Ergosphere. It lies outside the event horizon of a rotating black hole, not as a perfect sphere, but as a bulging zone pressed outward around the equator. At the poles, it touches closer to the horizon. Around the middle, where the spin has its widest reach, it swells farther away. The shape hints at the cause. Rotation has given the darkness a wider influence along its turning waist. Inside the Ergosphere, remaining still relative to the distant universe is no longer possible. A body may still avoid falling through the event horizon for a time. It may still have paths that lead outward, but it cannot stand motionless against the spin. To do so would require moving in the opposite direction faster than light relative to the local space, and that is not allowed. The black hole has not forced the body across the horizon yet. It has forced it to share the turning. This distinction is gentle but important. The Ergosphere is not the same as the event horizon. The horizon marks no return. The Ergosphere marks no stillness. Within it, escape may remain possible, but rest is gone. Space-time has become a river whose current cannot be cancelled by any ordinary motion. An object can steer within the flow. It can fall deeper or move outward. It can change its path, spend energy, lose energy, gain energy, but it cannot choose not to be carried around. Light follows the same curved rules. A photon passing near a rotating black hole does not simply bend toward mass in a symmetric way. Its path depends on whether it travels with the spin or against it. Light moving in the direction of rotation can skim closer before being lost. Light moving against the rotation meets a different geometry, a stronger resistance from the twisted paths around the hole. The shadow and bright ring of a spinning black hole therefore carry subtle signs of direction, as if the darkness has a grain in it. Just outside the horizon, another boundary appears in the mathematics of light. Photons can occupy unstable circular paths, racing around the black hole in orbits that cannot last. A slight inward shift sends them down. A slight outward shift lets them escape into space. This photon region is not a calm ring filled with orderly light, but a set of knife-edge paths where gravity and speed almost balance before balance breaks. Some of the light that reaches distant telescopes may have looped around the black hole once, or more than once, before leaving. Around a spinning black hole with hot gas nearby, these effects blend into a strange glow. Plasma in the disk orbits at high speed. Magnetic fields thread through it. Some material heats, some plunges inward, and some may be lifted into jets. The side of the disk moving toward a distant observer can look brighter because its light is compressed toward higher energies. The far side can be dimmer or shifted redder. Gravity bends the rear of the disk into view above and below the dark center, so the eye receives a picture that ordinary perspective could never make. The black hole itself remains unseen, but its spin is written into the surrounding motion. It may be read in the shape of a shadow, in the tilt of a disk, in the rhythm of matter orbiting close to the edge, or in the way jets align with magnetic fields near the center. No single sign is simple. Gas is turbulent, magnetic fields twist. Observations are hard. Still, the turning of the black hole leaves marks outside the place where light cannot return. There is a quiet strangeness in this. The speed of light is not broken locally. No nearby particle is allowed to outrun a photon passing beside it through the same small region. The old rule remains. Yet two regions of space-time can be arranged so that distant motion appears to stretch ordinary limits. The black hole does not let matter casually race faster than light through its own neighborhood. Instead, it changes the neighborhood. It drags the reference frame, bends the possible paths, and makes the question of motion depend on where the observer stands. This is one of the soft edges of intuition. In daily life, motion usually means a body crossing a background. Near a rotating black hole, the background has entered the story. The road moves. The compass of possible directions turns. The idea of staying still loses meaning before the idea of escape does. In that narrow region outside the horizon, the universe shows that geometry is not merely a diagram. It is a living condition for every path matter and light can take. Far from the black hole, a star field may look ordinary again. Distances open. The twisting weakens. Paths that were bent into curves relax into wider lines. The dark object becomes a small absence surrounded by vast space. But close to it, the old law of spin has become something deeper than a rotating surface or a turning world. It has become rotation in the shape of space-time itself, a slow dragging of reality around a center no light can reveal. The Ergosphere is a region of motion before it is a region of loss. It sits outside the event horizon, close enough for the black hole's spin to rule every path, but not so close that escape has vanished. Matter entering it is no longer free to remain still. Space-time itself is turning there, and anything that enters must be carried around. The way a leaf on deep water must share the motion of the current before it can drift away. For most falling matter, the journey is simple. Gas slips inward from a disk, heats as it rubs against other gas, circles faster, and finally passes the horizon. Dust follows. Broken fragments follow. Light may scatter from the surrounding plasma, but whatever crosses the dark edge no longer returns. In that familiar picture, the black hole only receives. It gathers mass, gathers energy, gathers the last signals of anything that falls too far. A rotating black hole adds a quieter possibility. Because the ergosphere still allows escape, a particle or body can enter the region, interact with the black hole's spin, and leave with more energy than it carried in. The extra energy does not appear from nowhere. It comes from the rotation of the black hole itself. The black hole gives up a little of its spin. The escaping fragment carries that borrowed motion outward into the wider universe. This idea is called the Penrose process. It is usually described with a particle that enters the ergosphere and splits into two pieces. One piece falls inward, crossing the event horizon with a special kind of negative energy as measured from far away. The other piece escapes. Because the falling piece reduces the black hole's rotational energy, the escaping piece can leave with more energy than the original particle brought in. In the accounting of the distant universe, something has been extracted from the darkness. The image can be softened into motion. A small, bright fragment descends toward a rotating black hole, not straight down, but into a region already being pulled around. Near the edge of no stillness, it breaks apart. One part is taken inward, lost beyond the horizon. The other is flung outward, brighter in its motion than before. The black hole remains black. No light has escaped from inside it, yet some of its spin has been transferred to matter that never crossed the final boundary. The process is delicate and severe in practice. It requires paths arranged with great precision near a place where gravity, speed, and curved geometry leave little room for error. Ordinary rockets cannot treat a black hole like a power station waiting beside a road. The nearest known black holes are far beyond any present reach. The region around many of them may be filled with radiation, hot plasma, magnetic turbulence, and tidal forces that would tear weak structures apart. A black hole with an accretion disk is not a quiet harbor. It is a deep center wrapped in light. Yet the idea does not depend on near-term use. It shows that a black hole is not only a one-way sink, its spin is a reservoir. Energy can be stored in the rotation of space-time around the horizon, and under the right conditions, some of that energy can be carried away. The old image of total destruction becomes less complete. A rotating black hole can give something back, not from within the horizon, but from the turning region, just outside it. Nature may already use related methods in a less tidy form. Around some black holes, narrow jets shoot outward across distances far larger than the system that launched them. These jets can pierce surrounding gas, inflate bubbles in galaxy clusters, and carry energy into space that would otherwise have remained near the central darkness. The exact mechanisms are complex, and magnetic fields are deeply involved. But many models draw on the same broad principle. A spinning black hole, surrounded by plasma and threaded by magnetic fields, can transfer rotational energy outward. In one picture, magnetic field lines behave like long, flexible threads anchored in the moving plasma near the black hole. As the black hole spins, the field lines twist. Charged particles respond to those twisted fields. Energy flows away along the magnetic structure, sometimes forming jets that travel close to the speed of light. The power does not come from a solid surface. It comes from rotation, magnetism, and curved space, working together in a region where ordinary separation between object and environment has nearly disappeared. This is not the Penrose process in its simplest particle form, but it belongs to the same family of thought. A black hole's rotation can be tapped, not casually, not cleanly, not like turning a wheel in a machine, but through the deep relationship between spin and geometry. Matter and fields near the horizon become translators. They convert the black hole's stored rotational energy into escaping motion, radiation, and sometimes jets. There is a strange gentleness in that exchange when viewed from far away. A galaxy may hold a bright core, where gas is falling toward a central black hole. Around that core, light flickers across years. Jets extend in thin lines, almost still from a human perspective, though the particles inside them move at enormous speeds. The black hole itself remains a silent center. Around it, the borrowed energy of spin writes long marks into space. This also changes the way faster-than-light dreams are often imagined. Nothing local outruns light. A particle beside another particle remains bound by the same limit. A spacecraft cannot simply press harder and cross the barrier through ordinary acceleration. But around a rotating black hole, space-time shows that motion is not always only about speed through a fixed background. The background can be shaped, the frame itself can be dragged. Paths that look impossible from one viewpoint may arise because the geometry around them has changed. The black hole does not hand over a practical engine for human travel. It offers a lesson more distant and more subtle. It shows that the universe permits forms of motion that ordinary experience does not prepare the mind to expect. Energy can be stored in rotation. Space-time can be twisted by mass. Escape and stillness can be separated into different boundaries. A dark object can take in matter, while also allowing its spin to power light outside the horizon. Near the Ergosphere, the old law of spin has become hidden inside the fabric of reality. It is no longer the turning of a planet or the swirl of gas around a young star. It is the turning of possible paths. It is a place where energy can be borrowed from darkness because the darkness itself has motion. Far from that region, the borrowed energy may appear only as a particle leaving faster than it arrived, or as a jet crossing interstellar space, or as a glow in the heart of a distant galaxy. The event horizon still marks the end of return. Nothing changes that quiet fact. But just outside it, in the turning zone where stillness is impossible, the black hole is not only an ending, it is also a reservoir of old rotation, a deep store of motion left behind by collapsing stars and falling matter. In the darkness around it, energy does not vanish into a simple silence. Some of it may be handed back to the universe, carried outward on paths shaped by spin. Light near a black hole does not leave in a simple way. It travels through curved space, through hot plasma, through magnetic fields that have been stretched and wound by motion. Some of it falls forever. Some of it escapes after being bent into a new direction. Some of it carries, in the direction of its vibration, a faint record of the conditions it has crossed. This record is called polarization. Ordinary light can be imagined as a crowd of waves vibrating in many directions at once. Polarized light is more ordered. Its waves share a preferred direction, as if the light has passed through a hidden comb that has aligned part of its motion. Near a black hole, that order can be produced by charged particles moving through magnetic fields. The light is not only bright or dim, it has an orientation. It has a grain. For a long time, black holes were known mostly by absence and by influence. Stars orbited something dark. Gas heated near something compact. Jets streamed from regions too small to explain by ordinary stellar engines. The horizon itself remained beyond direct sight. Then the Event Horizon Telescope joined radio observatories across Earth into a single instrument as wide as the planet, and the nearest surroundings of supermassive black holes began to take on shape. Not a photograph in the ordinary sense, not a clear view of a surface, but a ring of emission around a central shadow. The first ring around the black hole in Messier 87 gave astronomy a new kind of darkness. It showed a bright, uneven circle, formed by plasma glowing near the event horizon and by light bent along curved paths. Later, a polarized view of that ring revealed something quieter inside the glow. The polarization traced magnetic fields close to the black hole, fields arranged in arcs and bands, fields strong enough to help shape the motion of the surrounding plasma. The same kind of view later came from Sagittarius A star, the massive black hole at the center of the Milky Way. This one is much closer, but also much more restless in the sky of observation, changing more quickly as gas moves around it. Even so, the polarized light showed ordered magnetic structure near its edge. Across two very different black holes, one far away in a giant galaxy and one hidden in the crowded center of home, the light carried a similar kind of message. Magnetic fields near horizons may be organized, long-lived, and strong enough to guide the matter trying to fall. Spin is woven into this message, though not in a simple line. A black hole does not display a rotating surface. It has no continents, no sunspots, no visible mark that can be watched moving around from left to right. Its rotation must be inferred from the behavior of nearby light and matter. The plasma close to the horizon circles at high speed. Magnetic fields are carried, stretched, and twisted by that motion. Space-time itself is dragged in the direction of the black hole's spin. The escaping light passes through all of this before reaching distant instruments. A polarized image can therefore become more than a picture. It becomes a map of orientation. Each small region of the ring can hold a direction, a tiny line showing how the electric field of the light is aligned. Taken together, those lines can form swirls, arcs, or changing bands. The pattern depends on the magnetic field, the motion of the plasma, the viewing angle, and the spin of the black hole. No single feature speaks alone. The meaning comes from the whole arrangement. Close to the horizon, even the light that escapes may have taken more than one path. Some rays come from the nearer side of the plasma. Some are bent from behind the black hole into view. A few may loop around before leaving, adding thin, faint structures to the ring. These deeply bent paths are especially sensitive to the shape of space-time. In them, gravity has written more strongly. If future instruments can separate such light with greater care, the photon ring may become one of the cleanest traces of the black hole's geometry. The next generation of horizon-scale telescopes aims for that kind of clarity. More observatories, higher sensitivity, and shorter radio wavelengths may sharpen the view. The goal is not only to see a darker shadow or a brighter ring, it is to watch how the ring changes, how polarization shifts, how plasma moves, how magnetic fields hold their shape or lose it. A black hole's spin may then be measured not as an abstract number, but as a pattern of turning written into light. There is still caution in this work. Plasma near a black hole is not a neat laboratory. It is hot, thin, turbulent, and magnetized. Small changes in assumptions about the gas can change the inferred spin. A polarized spiral may suggest one kind of motion, then a different model may reproduce a similar image through another path. The science is powerful because it is careful. Around the ring, this patience matters more than speed. The signal is faint, the source is distant, and the smallest turn in the model can change what the pattern seems to say. It does not treat the ring as a simple answer. It treats the ring as a layered trace, and each layer must be separated slowly. The image itself remains gentle to contemplate. A dark center, not empty, but unreachable. Around it, a soft ring of radio light, uneven and blurred by distance, brightened on one side by motion, shaped by gravity on all sides. Across the ring lie small orientations of polarization, invisible to the eye, until instruments translate them. They resemble fine strokes laid over a halo, not decoration, but evidence. Each stroke belongs to a wave that survived the edge of extreme gravity. In that light, the black hole's spin becomes less like a hidden fact and more like a presence diffused through the surrounding world. It appears in the way matter circles. It appears in the way magnetic fields wind. It appears in the way polarized light bends and arrives, carrying an order that was shaped close to the horizon. The darkness remains dark. The interior remains silent, yet the region just outside it is no longer mute. A black hole cannot be opened. Its horizon cannot be crossed by any signal returning to describe what lies within. Still, the turning around it can be read, not perfectly, not finally, but with growing patience. The light that escapes has been touched by gravity, plasma, magnetism, and motion. It has passed near the last edge of return and come away bearing a trace. In the quiet ring around a black hole, the universe leaves a faint signature of spin, written not in ink or stone, but in the remembered direction of light. Betelgeuse glows in Orion, like a deep ember held in winter darkness. To the eye, it is only a reddish point, one star among the familiar marks of the hunter. Through instruments, it becomes something far larger and less settled. It is a red supergiant, swollen near the late stages of stellar life, with an outer atmosphere so extended that its edges are difficult to define cleanly. Its light does not come from a small, smooth surface. It comes from a vast, restless envelope of gas, rising and sinking under the pressure of heat from below. A star like this has left the steadier years of its life behind. Long ago, hydrogen fusion in its core supported a more compact body, but the balance changed as fuel was spent and new layers of burning took shape. The outer regions expanded. The surface cooled compared with hotter blue or white stars, giving the star its red color. The body grew so large that, placed at the center of the solar system, its outer layers would reach far beyond the orbit of the inner planets. Even that image is only approximate, because the edge of Betelgeuse is not sharp. It fades outward into atmosphere, dust, and flowing gas. Within that swollen body, rotation becomes difficult to picture. A solid globe can be imagined turning as one piece. A red supergiant is not a solid globe. Its outer layers are gas and plasma, stirred by enormous convective motions. Heat rises from deeper regions in broad cells. Cooler material sinks back down. The visible surface shifts, brightens, dims, and changes shape. A mark seen at one moment may not survive long enough to be used like a spot on a planet. To measure rotation here, astronomy must use light itself. The method begins with a quiet change in color. When material moves toward an observer, the light it emits is compressed into slightly shorter wavelengths, shifted toward the blue end of the spectrum. When material moves away, the wavelengths stretch a little, shifted toward the red. The same principle can be heard in sound when a passing siren rises and falls in pitch, though starlight carries the effect across space without air. In a rotating star, one side of the surface moves a little toward Earth, while the opposite side moves away. One half becomes faintly bluer, the other becomes faintly redder. For Betelgeuse, this kind of measurement has suggested motion that appears unexpectedly fast for such an expanded star. A giant body should usually rotate slowly at its surface. As a star swells, the same angular momentum is spread over a much wider radius, and the outer layers should ease into a slower turn. The image resembles a spinning skater stretching the arms outward, losing speed as the motion is carried farther from the center. Betelgeuse has seemed, in some observations, to resist that simple expectation. There are ways a star might gain extra spin. It may have been born with more angular momentum than expected. It may have interacted with another star. It may once have had a companion close enough for gas to flow between them, or close enough to be swallowed as the larger star expanded. Such an event would not leave a simple wound on the surface. It would leave motion, mixed into the outer layers, a memory of another body transferred into the swollen red star. The term often used is stellar merger or stellar engulfment, but the quieter image is of one star absorbing the last orbit of another. If that happened to Betelgeuse, its present motion might be part of a hidden history. The red surface would not merely be turning because the original star once turned. It would be carrying the angular momentum of a companion that no longer exists as a separate light. Matter from the smaller body would have been drawn in. Its orbit would have tightened. Its motion would have entered the larger star, helping the envelope rotate faster than a solitary red supergiant should. The possibility is graceful, but not settled. Betelgeuse is close by astronomical standards, yet it remains far enough that even powerful instruments see its surface with limited detail. Its disk is not the clean, textured face of a nearby planet. It is blurred, softened by distance, and by the star's own unsettled atmosphere. Measurements must be interpreted through models of gas, light, temperature, and motion. A pattern that looks like rotation may contain more than one kind of movement. The star also changes brightness in slow and uneven rhythms. Some changes come from pulsation, as the outer layers expand and contract. Some come from convection, with large hot regions rising and darker regions sinking or cooling. Some may come from dust forming around the star, briefly blocking part of its light before drifting away. During the great dimming seen in recent years, Betelgeuse faded enough to stir wide attention, then brightened again. The event did not signal an immediate end. It showed how alive the star's outer atmosphere can be. In the slow fire of Betelgeuse, surface motion is not a small detail. It is the visible language of the star's condition. Gas rises because heat is trying to escape. The atmosphere expands because the star's late life has pushed it outward. Dust forms because cooler material can gather into grains in the extended layers around the star. Rotation, pulsation, and convection overlap until the red disk becomes a changing field of motion rather than a single turning face. The color shifts used to measure rotation must pass through all of that complexity. A blue-shifted region may not belong only to a side of the star rotating toward Earth. It may also be a region where gas is rising. A redshifted region may not only be the receding half of a rotating surface, it may be sinking material, falling back into the stellar envelope. Betelgeuse, therefore, teaches a careful lesson. Motion seen in light is real, but its cause may not be simple. Even so, the old law of spin remains present. Whether the star is truly rotating quickly, or whether some of that apparent spin comes from the breathing of its surface, the light is carrying motion outward. Each wavelength shift is a small messenger from gas moving across a star so large that ordinary measures of scale begin to feel thin. The red point in Orion becomes a world of rising cells, drifting dust, slow expansion, and possible hidden companionship. At night, Betelgeuse can still seem calm. It does not flicker with its full physical life to the unaided eye. It rests in the shoulder of Orion, red and steady enough to feel familiar. Behind that steadiness, the star is changing. Its surface is lifting and sinking. Its atmosphere is shedding material into space. Its light is arriving with tiny differences that reveal motion across a distant, swollen body. The universe often hides speed inside stillness. A red star can look fixed while its outer layers move through immense patterns. A point of light can carry the trace of gas rising across a surface larger than the orbit of planets. Betelgeuse is not only a bright mark in a constellation, it is a slow fire near the end of a star's life, and in its red light, rotation becomes less like the turning of a wheel and more like a memory moving through flame. The surface of Betelgeuse is not quiet enough to behave like a marked globe. It is closer to a red ocean made of gas, light, and heat, with broad regions rising from below and sinking again into the star. No island remains fixed. No dark spot offers a simple handle for measuring a turn. The star changes as it shines, and the motion inside its outer layers can imitate other motions when seen from far away. On a smaller star like the Sun, convection already leaves visible signs. Hot material rises from below, spreads across the surface, cools, and sinks along darker boundaries. Through telescopes, the solar surface can look grainy, filled with cells of moving plasma. On Betelgeuse, the same kind of process is enlarged beyond familiar scale. A single convective region may cover a large part of the visible disk. One rising cell can be wider than the orbit of an inner planet, broad enough to change the brightness and color pattern of the star as a whole. The reason lies in the star's late life. Betelgeuse has expanded into a vast, low-density envelope, and its outer layers are no longer tightly held in the compact order of a younger star. Heat from deeper burning regions must still travel outward. It does so through radiation, through flowing gas, and through great convective motions that lift warmer material toward the visible surface. As the gas rises, it moves toward the observer. If that region faces Earth, its light shifts slightly toward the blue. When cooler gas sinks, or when material moves away across the far side of a flow, its light shifts slightly toward the red. These color shifts are the same kind used to infer rotation. That is where the difficulty begins. If one half of Betelgeuse appears a little bluer, and the other half appears a little redder, the simplest interpretation is a rotating surface, with one side approaching and the other receding. Yet a giant convective cell can produce a similar pattern. A broad upflow on one side and a broad downflow on another can paint the disk with red and blue regions that mimic a turning star. Distance makes the imitation easier. Betelgeuse is large, but it is still a star hundreds of light-years away. Its apparent disk is tiny, and even the best observations soften the sharpness of the surface. Fine details blur together. Separate patches of motion can merge into a smoother gradient. A star covered in uneven, boiling cells may then appear, after the blur of distance and instrument limits, like a more orderly object rotating from one side to the other. This does not mean the observations are careless. It means the star is hard. Astronomers must interpret light that has crossed hundreds of years of space, light that began in a moving atmosphere and arrived as a small disk at the edge of resolution. A pattern can be real without its first explanation being complete. The blue and red shifts are there. The harder task is deciding whether they describe global rotation, local rising gas, sinking gas, pulsation, or several motions layered together. Simulations help by building a star inside mathematics and allowing its surface to move. In those models, giant convective cells rise and fall across the face of a red supergiant. The model star is then blurred to match what a telescope would actually see from Earth. When this is done, the patchwork of motion can often become deceptively smooth. A surface that is not rotating quickly can produce a signal that resembles rapid spin. The false order appears only after the details have been softened away. The image is almost dreamlike. A red star boils in silence. Huge cells of gas swell upward, bright and warm, then spread and fade. Other regions sink back, darker and cooler. From close by, if such a view were possible, the surface would not look like a polished sphere. It would look alive with slow, enormous weather, with motions too large for ordinary storm language. From Earth, that same weather can be compressed into a few colors, a few measurements, a suggestion of rotation that may not belong to the whole star. Betelgeuse also breathes. Its outer layers expand and contract over time, changing the amount of light that reaches Earth. These pulsations do not happen like a solid ball growing and shrinking in perfect rhythm. They mix with convection, dust formation, and the uneven release of heat. One region may brighten while another dims. Material can be pushed outward far enough to cool and form dust, which then blocks part of the star's light before drifting away. The Great Dimming was one visible sign of this restless outer atmosphere, not an announcement of an immediate collapse. When all these motions overlap, the surface becomes a layered signal. Rotation may still be present. Betelgeuse almost certainly turns in some way, because no star forms from perfectly still material. But the measured speed of that turn may be hidden beneath the convective motions. The star's true rotation could be slower than some earlier interpretations suggested. The apparent spin may partly come from gas rising and falling in huge cells, making the surface pretend to be a wheel when it is more like a slow fire seen through a wavering veil. This kind of correction is not a weakening of the story. It makes the star more interesting in a quieter way. The first picture says that Betelgeuse may be spinning too fast. The deeper picture says that the star's surface is so large and unsettled that it can forge the appearance of fast rotation from its own internal weather. The mystery moves from one kind of motion to another. Instead of a single turning body, there is a red atmosphere full of broad currents, each one contributing to the light that leaves. The lesson reaches beyond one star. Astronomy often reads motion from light, but light can carry several motions at once. A galaxy's spectrum can hold the drift of stars, the flow of gas, and the pull of unseen mass. A black hole's ring can hold gravity, plasma, and magnetic fields together. A red supergiant's disk can hold rotation, convection, pulsation, and dust. The signal is never merely a message in plain language. It is more like a shoreline, seen through mist, true in outline, but needing patience before its shape is known. Higher resolution observations may separate these motions more clearly. Longer monitoring can watch patterns change across months and years. If a red and blue gradient holds its direction steadily, rotation becomes more likely. If the pattern shifts, breaks, and reforms with the rise and fall of cells, convection gains strength as the explanation. The star will not answer in a single instant. It will answer by changing slowly while instruments keep watching. For now, Betelgeuse remains both familiar and uncertain. A red point in Orion, a swollen star near the late edge of its life, a surface made of moving gas, where enormous cells can imitate the turn of the whole body. Its light arrives carrying motion that began in heat and depth, then crossed the dark between stars. In that light, the universe offers a careful reminder. Not every apparent spin is a wheel. Some turning is real, and some is the echo of a surface breathing under its own red glow. A massive star does not end quietly in the same form in which it lived. For millions of years, it may burn with great force, holding itself open against gravity through the heat released in its core. Layer after layer changes as fuel is spent. Hydrogen gives way to helium. Heavier elements gather deeper inside. The star becomes structured like a set of shells, each one shaped by pressure, heat, and the long contest between outward fire and inward weight. At last, for the most massive stars, the balance fails. The core can no longer support itself. Gravity, patient through the star's entire life, takes command in an instant. The center collapses. Matter falls inward with enormous speed. Electrons and protons are pressed together until they form neutrons. The empty spaces inside atoms, so large compared with the particles themselves, are crushed away. The outer layers rebound and are thrown into space as a supernova, leaving behind a remnant so dense that ordinary images begin to fail. A neutron star is that remnant. It may hold more mass than the sun inside a sphere, only about the width of a city. Its surface gravity is extreme. Its crust is made from forms of matter that cannot exist under normal conditions on Earth. Deeper inside, the pressure rises into states still studied through theory, observation, and careful uncertainty. The whole object is a collapsed core, a stellar ember made not of ordinary flame, but of compressed matter and leftover motion. The rotation of such an object can be astonishingly fast. The original star already had spin. Its core had spin. When the core shrinks from the size of a star to the size of a city, angular momentum is gathered inward, and the rotation quickens. A slow turn becomes a rapid one. A body that once took days to rotate may become a remnant turning many times each second. The old skater image returns, but now the skater is made from the heart of a dead star, and the drawn-in arms are the collapse of matter itself. This spin alone does not make a pulsar. A neutron star also carries a magnetic field, often far stronger than any field produced by a normal star. The cause is tied to the violent birth of the remnant, the compression of magnetic field lines, and the behavior of charged matter inside and around the star. The details remain difficult, but the result is clear enough in the sky. Some neutron stars become magnetic engines, sending radiation outward from their poles. The magnetic poles do not need to align with the rotation axis. Often they are tilted, the way Earth's magnetic north does not sit exactly on its geographic pole. As the neutron star turns, beams of radiation linked to those magnetic regions sweep around space. If one beam crosses Earth, a telescope detects a pulse. Then the star turns again, and another pulse arrives. The object becomes a lighthouse, not because it flashes on and off from its own surface, but because its beam repeatedly passes through the line of sight. From far away, this can seem almost impossibly regular. Pulse after pulse arrives with such steadiness that some pulsars have been compared to clocks. Their timing can be measured with great precision. Small delays may reveal a companion star. Gradual changes may show the pulsar losing energy. Tiny shifts can carry information about interstellar gas, orbital motion, or even waves in space-time passing between the star and Earth. A collapsed sun, no larger than a city, becomes a timekeeper spread across the galaxy. The pulses often come in radio waves, light with wavelengths much longer than the light visible to the eye. Radio telescopes gather these signals from the dark and translate them into timing, strength, and polarization. In that information, the hidden geometry of the neutron star begins to appear. A beam shape can be inferred. A magnetic field can be modeled. A rotation period can be measured again and again, each pulse another mark in a long sequence. The beam begins close to the magnetic poles, where charged particles move through intense fields. Electrons and positrons can be accelerated to high energies. Photons are produced. More particles can be created in cascades, multiplying the signal until radiation streams outward along open magnetic field lines. The process is severe, but from a distance it becomes simple in appearance. A repeating pulse, a small rise in the data, a quiet tick from a star that no longer shines, like the Sunday. There is great softness in the regularity when it is heard as a pattern rather than imagined as violence. A pulse crosses thousands of light years. It travels through cold space, through thin gas, past dust and magnetic fields, losing none of its rhythm except for small delays along the way. It reaches a dish on Earth, or an array spread across a desert, or an instrument listening in the radio dark. The star that made it may be ancient. The light may have left before many human histories began. Still, it arrives on time. Not every neutron star is a visible pulsar. Some beams never sweep across Earth. Some stars have slowed. Some may be too faint, too distant, or too hidden by the galaxy's crowded material. The sky contains many collapsed remnants that do not announce themselves in regular flashes. Their silence may only be a matter of angle. A lighthouse aimed elsewhere is still a lighthouse, though no observer on a distant shore sees the beam. Over time, a pulsar loses energy. Its rotation slows by tiny amounts as radiation and particle winds carry energy away. For young pulsars, the change can be more noticeable. For older ones, the ticking may remain steady over long periods, but the direction is still gradual loss. The star is spending the motion inherited from collapse. Its spin is not endless. It is a storehouse being emptied slowly into space. Some pulsars are made faster again by companions. In binary systems, a neutron star can pull gas from a nearby star. As matter spirals inward, it brings angular momentum with it, spinning the neutron star up until it rotates hundreds of times each second. These are millisecond pulsars, old remnants given a second life of rapid motion. Their regularity can be so fine that they become tools for measuring the galaxy itself, part of large timing arrays that listen for the faint stretching and squeezing caused by gravitational waves. The link between depth and precision is one of the quiet surprises of neutron stars. A supernova is disorder on a grand scale, an explosion bright enough to outshine galaxies for a time. Yet what remains can be steady, compact, and exact. Out of collapse comes rhythm. Out of destruction comes a clock. The universe does not always preserve calm by avoiding violence. Sometimes it makes calm from the remnants. In the wider story of spin, neutron stars mark a turning point. Planets rotate with days. Red supergiants move through broad, uncertain surface flows. Black holes drag spacetime itself. A pulsar gathers rotation into a signal, sending the memory of collapse outward as repeating light. Its beam sweeps through the dark, not hurried, not delayed, simply following the spin of a dense remnant that once burned as a star. Across the Milky Way, many such clocks are still turning. Some are young and slowing quickly. Some are old and precise. Some are hidden by geometry, their beams passing forever away from Earth. Each one carries the memory of a massive star's final inward fall. Each one turns in the silence after the explosion, sending, when the angle is right, a patient signal through the galaxy. Far beyond the nearest stars, in the crowded plain of the Milky Way, a radio source repeats with a rhythm that seems too slow for the kind of object it resembles. It does not flash many times each second like a young pulsar. It does not turn with the quick, sharp regularity of a collapsed core still rich with rotational energy. Instead, its signal returns after roughly 21 minutes, after a long pause by neutron star standards, followed by a pulse that can last half a minute or several minutes before fading again into the radio dark. The source is known as GPM, J1839-10. Its name is plain, more like a coordinate than a title, but the signal it marks has become one of the quiet puzzles in modern radio astronomy. It was identified in recent survey data, then traced backward through older observations, where the same repeating source appeared again and again across decades. The rhythm had been present for a long time, waiting inside stored measurements, not silent, only unnoticed. That long memory matters. A short-lived flare can be explained in many ways. A magnetic outburst, a disturbed binary system, or an unusual burst of plasma may shine briefly, then pass. GPMJ 1839-10 behaves differently because it persists. Its pulses appear across years separated by the length of ordinary human life. The source does not resemble a single spark. It resembles a clock that keeps breathing in the dark, slowly, patiently, with wide intervals of quiet between each return. The pulses themselves do not all look identical. Some are shorter, some last longer, some arrive brighter, then soften. They can appear within a window of time, rather than striking at one exact instant with mechanical sharpness. Even so, when many observations are gathered together, the deeper rhythm emerges. The source repeats near the same long period. Beneath the uneven surface of individual pulses lies a steadier cycle, as if a slow engine is turning somewhere far away, hidden inside a field of magnetized space. At first, the mind moves naturally toward pulsars. The signal is polarized, meaning the radio waves carry an ordered alignment. It repeats. It arrives from a compact source in the galaxy. These traits resemble the language of neutron stars, where intense magnetic fields and rotation send beams through space. If a beam sweeps across Earth, a telescope detects a pulse, then the beam passes on into darkness until the object turns again. That pattern has been known for decades, and many pulsars fit it beautifully. A normal pulsar is a collapsed stellar core. It forms after a massive star can no longer support itself, and its center falls inward, pressing matter into a neutron-rich state. The remnant is small by stellar standards, but heavy beyond ordinary imagination, with magnetic fields and rotation bound tightly together. Its beam is not like a lamp switching on and off. It is a path of radiation sweeping through space. The pulse appears only when that path crosses the line of sight from Earth. The 21-minute rhythm makes that familiar picture difficult. Ordinary radio pulsars tend to rotate quickly, often once every second or faster. Some older pulsars slow down, but as they lose rotational energy, their beams are expected to weaken. The magnetic engine needs enough spin and enough electrical potential to pull charged particles into motion, create cascades, and send radiation outward. If the rotation becomes too slow, the conditions for ordinary radio emission should fail. The star enters the region often called the Death Valley, where a pulsar should no longer shine as a regular radio source. GPMJ 1839-10 appears to sit beyond that expected boundary. If it is a neutron star rotating once every 21 minutes, then it is turning far too slowly for the usual pulsar picture. It should be quiet. The beam should have faded. The engine should have run down. And still the pulses arrive, long, ordered, and visible across a great distance. The signal seems to come from a clock that should have stopped. The slowness might be easier to accept if the object were losing energy quickly. A rapidly changing period could mean a strong magnetic field, a young or disturbed remnant, or some process still pouring energy into the emission. But the archival detections suggest stability. Across decades, the timing shows little sign of strong spin down. The object turns slowly, and it does not appear to be slowing in the way a simple model might require. It is faintly like finding a lantern burning after the fuel should have cooled, with no obvious source feeding the flame. The phrase, Death Valley, has a harsh sound, but the idea is calm. It is a boundary drawn on diagrams, a region where the ordinary pair production engine of a pulsar no longer works easily. Near the magnetic poles of a neutron star, charged particles must be accelerated strongly enough to create more particles and radiation. Those cascades help make the radio beam bright. Without enough rotational energy and magnetic potential, the cascade weakens, the lighthouse dims, the repeating signal falls away into silence. The new source appears to shine from the wrong side of that silence. It does not erase the old diagram. It asks whether the diagram is missing a path. Perhaps some neutron stars can produce radio emission by a different mechanism when their spin is slow. Perhaps magnetic fields can store and release energy in ways that do not depend entirely on rapid rotation. Perhaps the object is not a neutron star at all. Each possibility opens gently into another, with no need for a final answer too soon. One possibility is that the source is a magnetar. A magnetar is a neutron star, with a magnetic field far stronger than most pulsars. Its field can stress the crust, twist the surrounding magnetosphere, and release energy in bursts. Such objects are known for behavior that can look irregular, forceful, and difficult to fit into ordinary pulsar categories. They can produce radio emission for a time. They can flare in high-energy light. They can alter their signals as their magnetic fields rearrange. A slow magnetar might therefore seem like a natural place to look. Its magnetic field could provide energy even when rotation is not fast enough. The radio pulse might come from a twisted magnetosphere, rather than a standard pulsar beam. The object could be old, slow, and still capable of sending a signal because its magnetic field remains powerful. This explanation has a certain quiet appeal. It allows the clock to turn slowly without depending entirely on the fading store of spin. But magnetars bring their own difficulties. Their energetic disturbances are often accompanied by X-rays or other signs of high-energy activity. Their radio behavior can change, appear, vanish, and return. A decades-long pattern without the expected companion signals does not fall neatly into the usual magnetar story. The magnetar idea bends the rules, but it does not dissolve the puzzle. It changes the shape of the unknown. Another path leads to white dwarfs. A white dwarf is the remnant of a star that was not massive enough to collapse into a neutron star. It is dense, but much larger than a neutron star, closer in size to Earth than to a city. A white dwarf can rotate in minutes or hours without seeming impossible. Some white dwarfs carry strong magnetic fields. In rare systems, they can send out pulses as their magnetic fields interact with surrounding plasma or with a companion star. This explanation fits the slow period more gently. A white dwarf turning once every 21 minutes does not seem unnatural in the same way a neutron star does. Its larger size gives it a slower rhythm. Its rotation can remain stable over long periods. If it is strongly magnetic, and if the surrounding conditions are right, it may produce radio emission that arrives in pulses. The clock would no longer be too slow. The difficulty would move into the brightness and structure of the radio signal. To explain GPMJ 1839-10 as a white dwarf, the magnetic behavior would likely need to be unusual. The known examples do not easily match the source's radio power. A white dwarf answer may require an extreme object, a rare configuration, or an interaction not yet well represented in existing observations. It is a calmer body than a neutron star, but it still asks for conditions that are not ordinary. Binary systems offer another possibility. Two objects moving together can create rhythms that do not belong to either object alone. A magnetic white dwarf and a smaller companion may exchange plasma. A neutron star may interact with a nearby star through winds and fields. A compact object may pass through changing streams of material as it turns or orbits. In such a system, the 21-minute period might not be a simple spin period. It might be an orbital beat, a magnetic cycle, or a repeating interaction between two bodies. Such explanations can be rich, but they become crowded quickly. Each added piece must fit the same evidence. The signal must repeat on the observed timescale. The polarization must make sense. The pulse duration must be natural. The long-term stability must be preserved. The lack of obvious high-energy counterparts must be explained. Astronomy does not reject complexity, but it asks complexity to pay for itself with clarity. A binary model must not only be possible, it must make the strange source easier to understand. There is also the chance that long-period radio transients form a class that has only recently become visible to surveys. Radio astronomy is changing because instruments can now listen to wide fields of sky with greater patience and sensitivity. They gather enormous archives of data, full of faint events, repeating sources, and signals that earlier searches might have missed because they were not looking on the right timescale. A source that pulses every second is easy to catch with one kind of search. A source that waits 21 minutes between pulses requires a different kind of attention. The archive becomes part of the telescope. Old observations, stored for other purposes, can be searched again with new questions. A signal that once appeared as an isolated oddity may become meaningful when several appearances are placed side by side. GPM J1839-10 was not only discovered in the present, it was also recovered from the past. Its history had already been recorded, but the pattern had not yet been gathered. That is one of the quiet strengths of modern astronomy. The sky has already spoken in more ways than have been understood. Data sits in archives like sediment, layer upon layer, waiting for a new method or a new curiosity to expose a hidden trace. A slow radio pulse can lie there for decades. Then one source is recognized, and older layers begin to glow with the same rhythm. The signal itself invites patience. It rises out of radio silence, holds for a while, then fades. Between pulses, the source leaves only expectation in the instruments. There is no visible star to match the drama of the pattern. No bright nebula marks it for the eye. The object is known by timing, polarization, and recurrence. It is a presence made from return. In the larger story of spin, this source opens a door between known categories. It may be a neutron star using an emission process not yet understood. It may be a magnetar whose field powers radio light below the usual death valley. It may be a white dwarf with magnetic behavior stronger than expected. It may be a binary system writing an interaction into repeated radio waves. It may belong to a family of slow beacons that have always been scattered through the galactic plane, waiting for instruments patient enough to notice them. For now, GPM J1839-10 remains below easy explanation and above silence. Its signal crosses thousands of light years, arrives in patient intervals, and leaves behind a narrow mark in the data. Something compact is turning, pulsing, or interacting there. Something is keeping time where the usual clock should have gone quiet. In that slow rhythm, the Milky Way preserves another reminder that motion does not always end when theory expects stillness. The next slow beacon does not appear as a single mystery, but as part of a widening pattern. Once one long-period radio transient is found, the sky begins to look different. The old searches were shaped by known clocks, pulsars that tick in seconds or fractions of a second, flares that brighten once and fade, binaries that repeat with familiar orbital rhythms. A source that waits minutes or hours between pulses can slip between those expectations. It can be present in the data and still remain unnamed. Long-period radio transients are not defined by one object alone. They are sources that produce bright, often polarized radio bursts, then fall quiet, then return after intervals measured in minutes or hours. Some pulses last only seconds. Others linger for minutes. The emission may be strongly ordered, as if it comes from a magnetic region where charged particles move along guided paths. The periods are slow compared with ordinary pulsars, yet the radio brightness can be large enough to reach Earth from deep inside the galaxy. The class is still young. It does not yet have the settled shape of older astronomical families. White dwarfs, magnetars, neutron stars, and binaries all stand near the border of the explanation. Some sources may belong to one kind of object. Others may belong to another. The name long-period radio transient may therefore be a temporary shelter for several physical stories that only resemble one another from a distance. They repeat slowly. They shine in radio. They ask for magnetic fields. Beyond that, the family is still being sorted. A radio telescope listening at low frequencies can catch these beacons in a way optical telescopes cannot. The source may have no obvious visible flare. It may sit among countless faint stars, or behind dust, or in a region of the Milky Way where ordinary light is crowded and confusing. In radio, the sky becomes another landscape. The telescope records brightness across a wide field. It watches for changes. A point appears, fades, and appears again. The pulse may be short compared with the long gap that follows, but in that brief interval it becomes a mark in the map. The Murchison Wide Field Array has been especially useful for this kind of search because it watches large regions of sky at low radio frequencies. Its images can be revisited, stacked, compared, and searched again. A transient source does not need to be understood at the moment it first appears. It only needs to be recorded. Years later, when another pulse is recognized, older observations can be opened like stone layers in a cliff. The source may be found below, repeating before anyone knew it belonged to a pattern. This is how a new class begins to feel real. One object is strange. Two objects make the strangeness less lonely. Several objects begin to show range. Some repeat every few minutes. Others take hours. Some lie near the galactic plane, where massive stars and neutron stars are common. Others appear at higher galactic latitudes, where an isolated young magnetar becomes harder to imagine. The sky does not give the same clue twice. It gives partial clues, each one turning the question slightly. Among the slowest known examples, a source called Gleam XJ0704-37 repeats on a timescale of nearly 3 hours. That period is far beyond the normal rhythm of radio pulsars. Its radio pulses are strongly polarized, and an optical counterpart has been associated with a cool red dwarf star. The presence of that ordinary small star changes the story. A lone magnetar no longer feels like the simplest path. A binary system, possibly involving a white dwarf and a red dwarf, begins to move closer to the center of the explanation. In such a binary, the radio pulse may not come from the spin of a neutron star at all. It may come from interaction. A white dwarf with a strong magnetic field turns or orbits with a companion. The red dwarf gives off a stellar wind, a thin flow of charged particles. Where that wind meets the white dwarf's magnetic field, particles can be accelerated. Magnetic energy can be converted into radio emission. The system becomes a lighthouse, not because one dead core sweeps a beam alone, but because two bodies create a repeating magnetic encounter. This kind of picture is gentler in scale than a magnetar, but still powerful. A white dwarf is not a fragile ember. It is the dense core left by a star like the Sun, packed into a sphere roughly the size of Earth. Its surface gravity is strong. Its magnetic field, in some cases, can be intense. A red dwarf companion is small, cool, and long-lived, with magnetic weather of its own. Place them close together, and the empty space between them is no longer empty. It becomes a region of winds, fields, currents, and charged particles. The pulse period then may belong to an orbit, a spin, or a beat between the two. A beat occurs when two rhythms nearly overlap but not quite, producing a slower cycle from their difference. In a compact magnetic binary, the geometry can decide when the right field lines meet the right flow of plasma. For most of the cycle, the system may be quiet. Then the magnetic axis, companion wind, and line of sight fall into a brief arrangement, and radio light escapes. The pulse is not merely a flash. It is a moment of geometry. Other long-period transients may not fit that model. Some show properties that seem closer to magnetars, with polarization behavior and substructure that hint at a magnetosphere around a compact object. A magnetosphere is the region ruled by an object's magnetic field, filled with charged particles and shaped by rotation. In a neutron star or magnetar, the magnetic field can be so strong that it controls the motion of plasma with severe precision. A slow magnetar might produce radio bursts by magnetic stress, rather than by the ordinary pulsar engine. This possibility keeps the family open. The sky may be showing more than one route to slow radio pulses. One source may be a white dwarf binary. Another may be a long-period magnetar. Another may involve a neutron star interacting with surrounding plasma. The shared appearance would then be only the surface, a slow, polarized radio burst. Beneath it, the engines could be different, the way several kinds of storms can all send thunder across the same night. The search for counterparts becomes important. A radio source alone gives timing, brightness, polarization, and position. A visible or infrared counterpart can reveal a star. Spectroscopy can show whether that star moves back and forth, pulled in orbit by an unseen companion. X-rays can reveal hot, accreting gas. Gamma rays may hint at a more energetic, compact object. Each wavelength adds a layer, and the source slowly changes from a mark in a radio image into a physical system with bodies, fields, and motion. Some long-period transients have begun to show such counterparts. A red dwarf found at the radio position can suggest a binary. A matching orbital period can strengthen that case. A system with radio and X-ray emission may point toward accretion onto a white dwarf, where material from a companion spirals inward, heats, and shines. Yet even these clearer cases do not solve the whole class. They show that at least some slow radio beacons can come from white dwarf systems. They do not prove that all of them do. The population is small enough that caution remains part of the story. A dozen or so known sources can suggest patterns, but not final rules. Selection effects may shape what has been found. Low-frequency surveys favor certain kinds of emission. The cadence of observations favors some periods and misses others. Sources that pulse rarely may be overlooked. Sources that turn on only during active seasons may vanish before follow-up arrives. The known family may be only the bright shoreline of a much larger hidden coast. Future surveys will change the view. Wider fields, better cadence, and more sensitive instruments will find fainter pulses and longer periods. The square-kilometer array pathfinders, Meerkat, ASCAP, LOFAR, and other radio facilities are already making the low-frequency and transient sky richer. The Vera Rubin Observatory will add a deep optical record, helping identify faint companion stars that may sit at radio positions. Together, these instruments may sort the family into branches. For a sleep-bound story of cosmic motion, long-period radio transients offer a different kind of rhythm. They are neither rapid clocks nor single flares. They are slow returns. Their silence matters as much as their pulse. A telescope waits through the empty interval, and then the source rises again, carrying its ordered radio waves across space. The pattern feels almost tidal, an unseen system reaching the same arrangement again and again. The radio light itself is coherent, or nearly so in many cases, meaning the waves are organized in a way that ordinary thermal glow is not. This points toward processes involving magnetic fields and charged particles moving together, not just warm matter radiating because of its temperature. Coherent radio emission can be very bright. It allows small regions to be seen across large distances. A compact magnetic system can briefly outshine its quiet surroundings in radio, then vanish back into the field. Polarization deepens the clue. If the electric field of the radio waves is aligned, the emitting region must have order. Magnetic fields provide that order. Changes in polarization across a pulse can suggest that the beam is moving, or that the magnetic geometry is rotating, or that the light is passing through plasma that changes its orientation. The pulse becomes a small sweep-through structure. It has shape, not only brightness. The idea of a new family also changes the older story of pulsars. For decades, pulsars were the great radio clocks of the galaxy, most of them fast by human standards, many of them slowing gradually as they spent rotational energy. Long-period transients appear beyond that familiar territory. They do not replace pulsars. They widen the map around them. The galaxy now contains beacons that tick in seconds, in milliseconds, in minutes, and perhaps in hours, each rhythm tied to a different kind of compact motion. In the dark between pulses, nothing has ended. The white dwarf may still turn. The red dwarf may still shed its wind. The magnetar may still hold twisted fields above its crust. Plasma may still gather in invisible structures. The system is not asleep, only below the threshold of radio brightness. Then the geometry returns, and a pulse leaves, beginning a journey that may last thousands of years before it meets a telescope. There is comfort in the incompleteness of this science. The sources have names, periods, coordinates, and measurements. Yet their identities remain partly open. They are not empty mysteries built from absence. They are measured unknowns. They have pulses that can be timed, polarization that can be traced, counterparts that can be searched, and models that can be tested. The uncertainty is not fog without shape. It is a dim object, slowly gaining edges. The Milky Way is likely holding more of them. Some may already be stored in archives, waiting for a search tuned to the right rhythm. Some may be active now, pulsing between the attention of surveys. Some may lie in crowded fields, hidden by confusion, or at frequencies that have not yet been watched long enough. The family may grow from a handful of sources into a layered population of magnetic binaries, slow neutron stars, and hybrid systems not yet named. And so the story moves outward from one strange source to a wider listening. The galaxy is not filled only with bright stars and silent remnants. It also contains hidden magnetic clocks, some turning alone, some bound to companions, some perhaps powered by fields that have not yet been fully understood. Their radio pulses cross the dark in long intervals, each one a small sign of motion in a system too faint to see. The new family of slow beacons is still being gathered, one patient signal at a time. Geminga lies close by the standards of the galaxy, only about 800 light-years from Earth, yet for a long time it seemed almost absent. It was bright in a part of the spectrum human eyes cannot see, bright in gamma rays, but it gave little of the familiar radio signal that many pulsars use to announce themselves. Its name carries that strangeness. It comes from Gemini and gamma, and from a phrase in an Italian dialect meaning that it is not there. A fitting name for a source that shone strongly while hiding from the instruments that first knew how to recognize pulsars. In the sky, Geminga sits in the direction of the constellation Gemini, a quiet point embedded in the wider glow of the Milky Way. It is a neutron star, the collapsed remnant of a massive star that ended in a supernova hundreds of thousands of years ago. The explosion is gone. The star that came before it is gone. What remains is small, dense, magnetized, and moving fast through space, carrying the old force of its birth across the thin gas between stars. The first hints of Geminga came through gamma rays, light with far more energy than visible light. In the 1970s, satellite observations found an unknown source in that part of the sky, but the position was not precise enough to tell what object was responsible. The source stayed unresolved for years, bright enough to matter, hidden enough to resist easy naming. It was not a normal visible star. It was not an ordinary radio pulsar. It was a glow without a clear body. Later observations in X-rays narrowed the search. The source began to take shape across wavelengths, first as a high-energy presence, then as something that might pulse. When instruments finally revealed its rhythm, Geminga became clearer. It rotated a little more than 4 times each second, sending high-energy radiation into space as it turned. That period placed it among pulsars, but not among the usual radio-bright lighthouses known from earlier surveys. Most pulsars were first discovered through radio waves. Their beams sweep past Earth, and radio telescopes record pulse after pulse. Geminga did not behave that way. For years, it seemed almost radio silent, and that silence made it unusual. It was not silent in all light. It was one of the brightest gamma-ray pulsars in the sky. The missing radio voice was therefore not a sign of weakness. It was a sign of geometry, magnetic structure, or emission that did not reach Earth in the expected band. A pulsar's appearance depends strongly on angle. The beams of radio emission are usually tied to magnetic poles. Gamma-ray emission may come from broader regions farther out in the magnetosphere, near the star's rotational equator, or along outer magnetic gaps. If Earth lies in the path of the gamma-ray beam but not the radio beam, the pulsar appears bright in gamma rays and faint in radio. Another pulsar with a different orientation may show the reverse. The object has not changed its nature. The line of sight has changed the story. Geminga seems to be one of these geometric lessons. Its radio beams may not be aimed well toward Earth, or they may be weakened by processes in the magnetosphere. The gamma rays, however, reach this planet clearly. In that sense, Geminga is not hidden so much as sideways. It is a lighthouse whose strongest beam sweeps across Earth in high-energy light. while the older radio searchlight passes elsewhere or arrives only faintly. The neutron star is also moving. Like many stellar remnants, it received a kick during the supernova that made it. The explosion was not perfectly balanced, and the compact core was sent traveling through the galaxy at high speed. Over thousands of years, Geminga shifts across the sky by a small but measurable amount. The motion is tiny to the eye, yet real in the careful record of telescopes. A dead star is crossing the interstellar medium, leaving signs behind it. That motion shapes the space around the pulsar. A neutron star does not move through emptiness in a simple way. It carries a wind of charged particles, driven by rotation and magnetic fields. Electrons and positrons stream outward from its magnetosphere. As the pulsar travels through thin interstellar gas, its wind presses against the medium around it, forming a bow-shaped region, trails, and high-energy structures. In X-rays, Geminga has shown tail-like features, narrow signs of particles moving through magnetic fields behind and around the racing remnant. The particles matter because they connect Geminga to a wider puzzle near Earth. Instruments above the atmosphere have measured cosmic rays, including electrons and their antimatter counterparts, positrons. A positron is the antiparticle of an electron. It has the same mass, but opposite charge. When positrons are found in space, they can come from known processes such as cosmic ray collisions with interstellar gas, but observations have shown more high-energy positrons than those ordinary sources easily explain. For years, that excess attracted several possible explanations. Some look toward dark matter, because certain dark matter particle models could produce positrons when particles annihilate or decay. Others look toward nearby pulsars, because pulsars naturally accelerate electrons and positrons in their magnetic environments. The question was not whether pulsars can make such particles. They can. The harder question was whether enough of those particles could escape, travel through the galaxy, and arrive near Earth with the energies observed. Geminga became important because it is both close and old enough to have released particles over a long time. Its age allows positrons and electrons to spread outward. Its distance is small enough, in galactic terms, that some of those particles might reach the solar system. If Geminga has been injecting high-energy particles into the surrounding medium for hundreds of thousands of years, then it could contribute to the local cosmic ray population. The key evidence came from gamma-ray halos. High-energy electrons and positrons do not travel silently if they meet fields of light. They can collide with low-energy photons from starlight, infrared glow, or the cosmic microwave background, giving those photons extra energy. This process lifts the photons into gamma rays. A cloud of energetic particles around a pulsar can therefore reveal itself as a broad halo of gamma-ray emission, even when the particles themselves are invisible. The high-altitude Water-Cherenkov Observatory detected very high-energy gamma-ray emission around Geminga and another nearby pulsar. The results showed that energetic particles were present around these pulsars, but it also raised a difficulty. The particles appeared to diffuse slowly near the source. If diffusion were that slow everywhere between Geminga and Earth, then fewer positrons would reach the solar system than needed to explain the excess. The pulsar answer became less simple. Later, the Fermi Large Area Telescope looked at lower-energy gamma rays over a much broader region. After other sources and background emission were carefully modeled and removed, an extended glow around Geminga appeared. This halo was much larger across the sky, spreading over a region that would look enormous if human eyes could see gamma rays. The size and energy of the glow suggested that particles from Geminga may travel through a larger surrounding zone, and that the pulsar could still contribute meaningfully to the positron excess measured near Earth. In that picture, Geminga alone may account for as much as about 1/5 of the high-energy positrons detected by space-based instruments. That does not make it the whole answer. It makes it a strong local contributor. If one nearby pulsar can provide such a share, then the combined output of many pulsars across the galaxy becomes a natural explanation for much of the excess. The antimatter reaching Earth may not need an exotic origin. It may be the dust of dead stars, charged and accelerated, crossing space in streams too thin to see. There is care in that statement. The halo is faint and broad, and the galactic background is difficult to model. Gamma-ray maps are filled with overlapping sources, diffuse emission, cosmic ray interactions, and instrument limits. A broad glow can be real, and still hard to measure precisely. Later analyses continue to test how strong the Geminga halo is at different energies, how much depends on background models, and how particle diffusion changes with distance from the pulsar. The question is not closed like a sealed box. It is being refined. That refinement belongs naturally to the story. A pulsar halo is not a sharp ring on a black sky. It is an extended region of particle motion, magnetic influence, and scattered gamma rays. Its edge is gradual. Its brightness fades into background emission. Its shape may be stretched by Geminga's proper motion through space, because the pulsar has not stayed in one place while injecting particles. It has moved, and the particles left behind remember that motion in the shape of the glow. The image is slow and wide. A neutron star, only the size of a city, travels through the local galaxy. Around it, electrons and positrons spread outward, some trapped near the source, some wandering farther into interstellar space. They meet soft fields of light and lift that light into gamma rays. A halo forms, not with a bright, visible edge, but as a broad, high-energy mist, drawn over decades of observation by instruments above and on Earth. Geminga's near silence in radio makes this halo feel even more fitting. The pulsar is not loud in the old way. It does not dominate radio surveys with a strong beam. Its presence is revealed instead through high-energy light, X-ray trails, motion across the sky, and the particle cloud around it. It is a source understood by indirect signs, each sign adding one calm layer to the picture. In the story of cosmic rotation, Geminga shows how spin can travel outward after the star itself has died. The neutron star's rotation powers its magnetosphere. The magnetosphere accelerates particles. The particles form winds, tails, and halos. Some may eventually arrive near Earth as cosmic rays. The original turning of the collapsed core becomes a dispersed influence across light-years of space. Spin becomes radiation. Radiation becomes particles. Particles become a glow too broad for the eye. The positrons themselves do not arrive with labels. A detector near Earth records charge, energy, and direction only imperfectly. It cannot point to one particle and name Geminga as its source. The connection is made through populations, models, halos, distances, ages, and energy spectra. It is a work of reconstruction. The galaxy sends many particles from many places, and astronomy tries to separate the river into its tributaries. Geminga is one of the clearest tributaries, because it is near, energetic, old, and surrounded by measurable high-energy emission. It does not solve every particle mystery. It does not close the dark matter question. It simply shows that ordinary astrophysical engines can produce a great deal of what once seemed to require something more hidden. Dead stars, through their magnetic fields and rotation, may fill local space with more antimatter than expected. There is a quiet balance in that idea. Antimatter sounds distant and strange, but here it may come from a nearby stellar remnant, a familiar kind of object made after the death of a massive star. The particles that touch the upper atmosphere may have begun near a neutron star in Gemini, accelerated by fields around a body no wider than a city, then carried outward through the thin medium between stars. Their journey is long, but not mystical. It is written in charged motion and light. Geminga remains a soft contradiction. It is nearby, yet hard to see. It is quiet in radio, yet bright in gamma rays. It is small, yet surrounded by a halo covering a large area of the sky. It is a dead star that still sends motion outward in particles and radiation. Its name says it is not there, but its traces are everywhere that instruments know how to listen. As the story leaves the slow radio beacons and moves through Geminga's broad, high-energy glow, the scale opens again. A single collapsed core becomes part of the local environment around Earth. The turning of a neutron star becomes a possible source of antimatter rain. The Milky Way is no longer only a band of stars overhead. It is a field of old engines, faint halos, and invisible particles moving through the dark, carrying the memory of stellar deaths across the quiet spaces between suns. A galaxy looks, at first, like a single object. A spiral galaxy especially can seem almost designed for that illusion, with a bright center, a flattened disk, and arms curling outward through blue stars and lanes of dust. In a still image, the shape appears fixed, as if the whole structure might rotate like a wheel. The eye sees the curve, the center, the symmetry, and quietly expects a solid turning body. A galaxy is not solid. It is a population of stars, gas clouds, dust, stellar remnants, dark matter, magnetic fields, and radiation, all bound together by gravity, but not locked into one rigid piece. Each star follows its own orbit around the galactic center. Each gas cloud drifts, collides, cools, warms, and sometimes collapses into new stars. The disk may have a shared direction of motion, yet the material inside it does not turn like a painted mark on a spinning plate. This difference matters because a spiral arm is not simply the same group of stars forever. If it were, the galaxy would wind itself tighter with time. Stars closer to the center usually complete their orbits more quickly than stars farther out. A fixed material arm, stretched across those different orbital speeds, would soon be wrapped into a narrow coil. Spiral galaxies have existed for far longer than such a pattern should last. The arms remain open, broad, and recognizable. Something else is keeping the shape. That problem is sometimes called the winding problem. It begins with a simple expectation and ends by showing that the visible spiral must be more subtle than a solid feature. The arms are not long handles attached to the center. They are not carved ridges. They are more like regions through which stars and gas pass, a pattern moving through the disk rather than a permanent set of objects. The arm is real, but its material membership changes. The leading explanation describes spiral arms as density waves. A density wave is a region where matter is slightly more crowded than nearby space. Stars and gas enter it, slow or bunch up under gravity, then pass through. The pattern can remain while the individual stars move on. A road with a slow patch of traffic offers a small earthly comparison, though the scale is far too small and the physics only partly overlaps. Cars enter the slow region, spend time there, then leave. The traffic jam can remain in roughly the same place even though its cars are replaced. In a galaxy, the density wave is shaped by gravity. Stars orbit through the disk, and their collective pull can form a long-lived pattern. Gas responds more strongly because it can collide, compress, cool, and form clouds. When gas enters a spiral arm, it may be squeezed enough to trigger star formation. New stars appear there, and the brightest among them are hot, blue, and short-lived. They shine strongly but burn through their fuel quickly. Many do not live long enough to travel far from the arm where they were born. This is why spiral arms are bright. They are not bright only because they contain more stars. They are bright because they contain young stars, glowing gas, and star-forming regions. Pinkish nebulae mark hydrogen lit by newborn stars. Dark dust lanes trace cooler material where future stars may gather. The arms become visible not as fixed structures, but as zones of birth. The pattern organizes gas, and gas makes the pattern shine. Older stars tell a softer story. They are spread more broadly through the disk, including the spaces between arms. Many are cooler and dimmer than the young blue stars that outline spiral structure. In infrared light, where older stars become easier to see through dust, a galaxy may look smoother. The dramatic arms, seen in visible light, become part of a deeper disk, filled with stars that have already passed through many patterns of crowding and release. The spiral pattern itself may be steady in some galaxies and temporary in others. Some arms may be driven by interactions with companion galaxies. A passing neighbor can tug on a disk and raise a wave, much as the moon raises tides in Earth's oceans, though on a much larger and slower scale. Some spirals may be maintained by a central bar, a long structure of stars crossing the core and stirring the disk outward. Some arms may be transient, forming, breaking, and reforming across hundreds of millions of years. There is no single spiral story for every galaxy. Grand design spirals show two clear arms, sweeping around the disk with a calm, visual order. Flocculent spirals look softer and patchier, with many broken arm segments. Barred spirals send arms outward from the ends of a bright central bar. The Milky Way itself is a barred spiral, though its full shape must be reconstructed from inside the disk, through dust, distance, and the positions of stars and gas clouds. Living inside a galaxy makes its pattern harder to see. The rotation of a galaxy brings another quiet surprise. In the solar system, planets farther from the Sun move more slowly in their orbits. This makes sense because most of the mass is concentrated in the Sunday. At larger distances, the Sun's pull weakens, and orbital speeds decline. Early expectations for spiral galaxies were shaped by a similar intuition. Stars far from the bright center were expected to orbit more slowly, because most visible matter seemed concentrated toward the middle. Observations showed something different. In many spiral galaxies, stars and gas far from the center move at speeds that remain nearly flat instead of falling sharply. The outer disk turns too quickly for the gravity of visible stars and gas alone. The stars do not fly away, so some additional gravitational influence must be present, or gravity must behave differently on galactic scales. The standard explanation is dark matter, an unseen mass component surrounding galaxies in large halos. Dark matter does not shine, absorb, or reflect light in ordinary ways. It is known through gravity, through the motion of stars, the bending of light, the structure of galaxy clusters, and the large-scale pattern of the universe. Around a spiral galaxy, a dark matter halo can provide extra gravitational pull at large distances, allowing outer stars to move faster than visible matter alone would allow. The galaxy is therefore not only the glowing disk in photographs, it is embedded in a wider, unseen structure. This unseen halo changes the feeling of galaxy rotation. The visible spiral becomes the bright inner part of a larger gravitational system. Stars travel through a disk held not only by the light that can be photographed, but by mass that remains dark. Gas clouds orbit inside a field, shaped by both ordinary and unseen matter. The arms, bars, and star-forming regions are surface features of a deeper arrangement. There are alternative ideas, including modifications to gravity at low accelerations, and such ideas have been explored for decades because rotation curves are so striking. The dark matter picture, however, connects galaxy rotation with many other observations across cosmology. It helps explain the behavior of galaxy clusters, the pattern of cosmic microwave background fluctuations, and the growth of structure over time. The rotation of a single galaxy therefore points outward to the architecture of the universe as a whole. Still, the visible disk carries its own local histories. Some galaxies rotate in ways that reveal past encounters. A spiral may have arms that appear to lead rather than trail. In most spiral galaxies, the arms trail behind the direction of rotation, like loose curves pulled by the motion of the disk. A galaxy known as NGC 4622 has been studied as a rare case where outer arms appear to lead. Such a shape is difficult to produce in a calm, isolated disk. It suggests disturbance, likely from a past interaction or merger. A merger does not need to destroy a galaxy completely to alter its motion. A smaller galaxy can pass through or be absorbed, adding stars, gas, and angular momentum in a new direction. The disk may warp, tidal tails may stretch outward, gas may be driven inward toward the center, feeding bursts of star formation. Arms may be pulled into odd shapes. Long after the visible encounter has faded, the rotation can preserve evidence of the disturbance. The Black Eye Galaxy offers another example of layered motion. It contains a dark band of dust near its center, giving the galaxy its common name. More deeply, it contains gas rotating in a direction opposite to other material in the system. Counter-rotating gas is a sign that galaxies can acquire matter from outside, perhaps through a merger, or through the slow capture of intergalactic gas. The galaxy then holds two histories at once, the older stellar motion and the newer gas flow moving against it. Such systems show that a galaxy is not born once and then left alone. It continues to gather, lose, and rearrange matter. Gas can fall in from the surrounding medium. Dwarf galaxies can be absorbed. Stars can be scattered into halos and streams. The disk may regrow after disturbance if enough gas remains. Rotation is therefore not a single inherited motion, but a record that can be edited by later events. Elliptical galaxies make the contrast clearer. They lack the bright spiral arms and cold gas-rich disks of active spirals. Many contain older stars moving on more varied, elongated paths. Some rotate slowly. Others show more ordered motion, but rarely with the graceful disk pattern of a spiral. Their shapes often come from mergers, where two or more galaxies have combined and scrambled many of the old circular orbits. The result can be a smooth glow, pale and broad, with little fresh star formation because much of the cold gas has been used, heated, or expelled. Between spirals and ellipticals lie lenticular galaxies. These have disks and central bulges, but little of the gas needed for strong spiral arms. They can look ghostly, with a smooth disk where star formation has quieted. A lenticular galaxy may be a spiral that has lost or exhausted its gas, or a system altered by environment inside a cluster. Its rotation remains, but the bright signs of new stellar birth have faded. The wheel-like illusion becomes even weaker because the old disk turns without the luminous arms that once made its motion easy to imagine. Galaxy clusters add another layer. In dense clusters, galaxies move through hot gas and through the gravitational influence of many neighbors. A spiral entering such a cluster can lose gas as it moves, stripped by pressure from the thin medium between galaxies. Without gas, the spiral arms lose their young stars over time. The disk may remain, still rotating, but the blue light fades and the galaxy becomes quieter. Motion continues after the visible drama has passed. The Milky Way carries all these themes in its own manner. Its stars orbit the galactic center, where a supermassive black hole sits within a dense environment of stars and gas. Its spiral structure is inferred from radio maps of hydrogen, from young stars, from dust, and from stellar distances measured with increasing care. Its disk is not perfectly flat. It is warped at the edges. It holds streams from smaller galaxies. It carries the remains of old mergers in the motions of stars now mixed through its halo. The Sun moves within this system, orbiting the galactic center over a period of hundreds of millions of years. During one such circuit, Earth changes completely at the surface. Continents drift, seas open and close. Ice ages come and go. Life evolves into forms that would not recognize the sky from earlier turns. The Sun's galactic orbit is steady on human scales, but it belongs to a path long enough to hold many histories of the planet. To look at a spiral galaxy, then, is to see a pattern that is both moving and persistent. The arms are real, but they are not fixed material arms. The rotation is real, but the galaxy is not a wheel. The outer stars move too quickly for visible matter alone, pointing toward a dark halo. The gas forms stars where waves compress it. The stars pass through, age, and drift onward. The galaxy keeps its shape not by remaining unchanged, but by allowing motion to renew the pattern. This is the gentler truth behind the photograph. A galaxy is a slow weather system of gravity. Its clouds are molecular gas. Its storms are star-forming regions. Its winds are stellar feedback and outflows. Its currents are stellar orbits and dark matter's unseen pull. The spiral arms are not painted onto it. They are waves passing through it, bright where new stars have recently formed, and dimmer where older stars have moved on. Across the universe, countless galaxies turn without turning as solid things. Some keep open spirals, some are barred, some are warped by neighbors, some carry gas against the direction of their stars, some have lost the material that once made their arms bright. Each one is a record of formation, disturbance, gravity, and time. Their shapes are not frozen designs, they are long-lived motions made visible by light. The story of spin has now widened from compact remnants to stellar cities. A neutron star can send a pulse with each turn. A black hole can drag space near its horizon. A red giant can let convection imitate rotation. A galaxy spreads motion across billions of stars, turning not as a body, but as a pattern sustained by orbits, waves, gas, and unseen mass. In the dark between galaxies, the same law remains patient. Matter keeps the motion it was given, and gravity shapes that motion into forms large enough to hold whole worlds inside their slow, luminous curves. Beneath the quiet surface of Earth, deeper than roots, deeper than ocean floors, deeper than the slow drift of continents, the planet carries a hidden motion of metal. The ground feels solid because the crust is cool enough to hold its shape, but far below that crust the world changes. Rock grows hotter, pressure rises, the mantle moves over great stretches of time. Still deeper, around the solid inner core, there is an outer core made mostly of liquid iron and nickel, flowing in darkness under heat and weight. This deep metal sea is not open water. It cannot form waves under a sky. It does not reflect stars. It is a hidden ocean under thousands of kilometers of rock, heated from below, cooled from above, stirred by the planet's rotation, and by the slow release of heat from Earth's interior. Its movement is one of the reasons a compass needle turns. Its motion helps create the magnetic field that surrounds the planet, a field that reaches outward into space and bends the path of charged particles from the sunday. The magnetic field is not a painted shell. It is invisible, dynamic, and uneven. Near the surface, it can be drawn as lines emerging near one magnetic pole, curving around the planet, and returning near the other. That drawing is only a simple guide. The real field is lumpy, changing, tilted, and alive with small variations. It shifts year by year. It weakens in some regions and strengthens in others. It is shaped by flows no eye can see, inside a layer no instrument has ever touched directly. The process is called the geodynamo. In its simplest form, it begins with electrically conducting liquid metal moving inside a rotating planet. Heat helps drive convection. Hotter material rises, cooler material sinks. Earth's rotation bends those flows into spiraling columns and broad patterns. Moving conductive material generates magnetic fields, and magnetic fields influence the moving material in return. The system feeds back on itself. Out of heat, rotation, and metal, a planet makes a magnetic shelter. That shelter matters. Charged particles from the sun stream constantly outward as the solar wind. During solar storms, the flow can grow stronger, carrying energy that disturbs Earth's magnetic environment. The magnetic field guides many of those particles around the planet or into polar regions, where they can light the upper atmosphere as auroras. The atmosphere also provides protection, absorbing and scattering radiation, but the field is the first wide barrier, a vast structure extending far beyond the surface. The magnetic poles are not fixed to the geographic poles. The geographic poles are tied to the planet's rotation axis, the points around which Earth turns. The magnetic poles belong to the field made by the core. They wander because the flow in the outer core changes. The North Magnetic Pole has moved markedly since it was first carefully located, drifting away from the Canadian Arctic toward Siberia. This drift is not a reversal by itself. It is one sign that the magnetic field is a living system rather than a permanent mark. The field also changes strength. Over recent centuries, measurements show a general weakening of the dipole portion of the field, though not in a way that proves a reversal is beginning. The past contains many intervals when the field grew weaker or stronger, without completing a full flip. A changing magnetic field is normal for Earth. The geodynamo is not a clock with a tidy period. It is a deep fluid system, and fluid systems can wander. In one region, the wandering is especially clear. The South Atlantic anomaly is a broad area where the magnetic field is weaker than expected, stretching over parts of South America and the South Atlantic. Spacecraft passing through this region encounter higher radiation because the inner radiation belt dips closer to Earth there. Satellites may shut down sensitive instruments. Astronauts in orbit receive careful monitoring. The anomaly is not a hole in the atmosphere, and it is not a sign that the surface below is exposed to open space. It is a region where the magnetic shield is thinner for objects above the planet. The anomaly likely reflects complex magnetic structure near the boundary between the core and the mantle. In some areas, magnetic flux appears reversed relative to the main dipole field, weakening the total field above. These reversed patches can grow, shift, and fade as the outer core moves. The surface expression is slow, broad, and measurable. It is one more reminder that the field is not a perfect bar magnet hidden inside Earth. It is a changing pattern created by flowing metal. Long before satellites and compasses, the field left records in stone. When lava cools, small magnetic minerals inside it can align with the direction of Earth's magnetic field at that time. Once the rock solidifies, that alignment becomes locked in place. Sediments can also preserve magnetic directions as tiny grains settle and become buried. Across many layers, these preserved directions create an archive of past magnetic fields. That archive shows that Earth's magnetic field has reversed many times. Magnetic north and magnetic south have exchanged places in the geological past, not once, but repeatedly. On the ocean floor, bands of rock on either side of mid-ocean ridges preserve alternating magnetic polarities. These patterns helped reveal seafloor spreading and became part of the evidence for plate tectonics. The magnetic field, changing above, became a key to understanding the moving crust below. A reversal does not happen like a switch turning in a room. The field weakens, becomes more complex, and may develop several temporary poles. The simple dipole pattern fades. Local structures grow more important. Magnetic north may wander far from the Arctic. Magnetic south may become hard to define. The whole field can pass through a long interval of confusion before a new dominant orientation emerges. When the system settles, the polarity may be opposite to what it was before. The timing is irregular. Some intervals between reversals are short by geological standards. Others are very long. There have been long supercrons, stretches of tens of millions of years, with no full reversal. The last full reversal occurred hundreds of thousands of years ago, but that does not mean the next one follows an appointment. Earth does not keep a simple reversal calendar. The geodynamo changes through chaotic motion, influenced by heat flow, core structure, mantle conditions, and the rotation of the planet. There are also excursions, shorter events in which the field weakens and magnetic poles wander far from their usual positions without completing a lasting reversal. The last comp event, around 42,000 years ago, is one of the best-known examples. During that interval, the field weakened strongly and the magnetic geometry changed for a time, then recovered. Such events are useful because they show how the shield can behave during periods of low strength without requiring a permanent flip. The effects of such weak field intervals remain a subject of careful study. A weaker field allows more energetic particles to enter parts of near-Earth space and the upper atmosphere. It can increase production of certain isotopes, such as radiocarbon, leaving traces in tree rings, ice cores, and sediments. It may alter the distribution of auroras and change radiation conditions for satellites or high-altitude systems if such technology exists at the time. In the deep past, there were no satellites, no power grids, no aircraft routes, and no orbital crews. The biological and climatic consequences are harder to separate from other changes happening at the same time. Some researchers have proposed that the Lascombe event contributed to broader environmental stress, especially when combined with unusual solar activity. Others have challenged the strength of that connection, noting that geological, archaeological, and genetic records do not clearly show a global crisis caused by the magnetic excursion alone. This debate is important because it keeps the story from becoming too simple. A weak magnetic field can matter. It does not follow that every weakening becomes a planetary disaster. The record of full reversals also argues for caution. Life has passed through many magnetic reversals. Forests, oceans, insects, reptiles, mammals, and countless microorganisms continued through them. The fossil record does not show a clear pattern of mass extinctions tied to each reversal. This does not make reversals meaningless. It means their effects are layered, local, gradual, and filtered through atmosphere, climate, biology, and chance. Earth is protected by more than one system. For modern civilization, the concerns would be different from those of the ancient biosphere. Satellites depend on electronics, vulnerable to radiation. Power grids can be disturbed by geomagnetic storms. Communication and navigation systems rely on space-based infrastructure. A weaker magnetic field would not remove the atmosphere, and it would not cause the ground to burn under cosmic rays, but it could make near-Earth space harder for technology. The danger would be practical, not mythic. A reversal would also unfold, slowly compared with a human emergency. Even a fast transition in geological terms would likely span many generations. Magnetic maps would need regular updating. Satellite design would adapt. Power systems would be hardened against space weather. Radiation monitoring would become more important for orbit, aviation, and polar routes. Human societies are vulnerable to sudden shocks, but they are also capable of adjusting to slow environmental change when the change is understood. The field's present behavior is therefore watched with great care. Observatories on the ground measure direction and strength. Satellites map the field from orbit. Models separate contributions from the core, crust, ionosphere, magnetosphere, and oceans. The result is not a prophecy of a coming reversal, but a living map of a changing planet. Each update adds detail to the motion of the hidden metal sea. There is a quiet beauty in the connection between the core and the sky. Liquid iron moves in darkness thousands of kilometers below the surface. That motion creates magnetic structure that reaches into space. Charged particles from the sun follow those structures and glow in the upper atmosphere. A flow no one can see produces lights that ripple above polar snow. The deepest Earth and the outer edge of the atmosphere are joined by invisible lines. The story also returns to spin. Without Earth's rotation, the geodynamo would not organize itself in the same way. The Coriolis effect helps shape rising and sinking flows into patterns that can maintain a global magnetic field. The turning of the planet gives structure to the motion of its core, in the same way that spin shapes disks around young stars, jets near black holes, beams from pulsars, and waves in galaxies. Earth's rotation helps shape the shield around life. This shield has never been perfectly steady. It flickers over centuries, wanders over millennia, reverses over deep time, and carries small regional weaknesses like weather inside the field. The compass needle gives the impression of certainty, but the needle is following something alive. Its north is not eternal. Its direction is in agreement with the present state of the core, an agreement that has changed before and will change again. At the surface, the day continues in ordinary ways. Oceans move under the moon, winds cross continents, cities brighten at dusk, birds navigate by many cues, including magnetic ones, but not by magnetism alone. Humans read maps, satellites, trace orbits, and instruments quietly correct for a field that never stops shifting. Beneath all of it, liquid metal keeps moving through pressure and heat, carrying the old planetary rhythm forward. The journey from black holes to Betelgeuse, from neutron stars to Geminga, from spiral galaxies back to Earth, ends not with a still world but with a hidden turning beneath the feet. Earth is part of the same family of motion. Its core flows, its field drifts, its poles wander. Its magnetic memory is stored in cooling lava and ocean crust. Even the planet that feels most familiar is not fixed in the way it first appears. Night falls again over the surface. The stars seem steady. The compass settles. The ground holds its shape. Far below, iron moves in darkness, and far above, the magnetic field opens into space like a quiet shelter. The planet turns once more, carrying its oceans, clouds, forests, cities, and sleeping life through the solar wind. Around it, the invisible field bends and breathes, changing slowly, protecting imperfectly, and remembering in its motion that Earth, too, belongs to the turning universe. After the long passage through turning darkness, the story settles again near the surface of Earth. The same planet that carries oceans and mountains also carries hidden motion below. And above it, the same sky holds stars, whose light began traveling long before this quiet night. Nothing in that sky is truly still, yet from the ground it can feel calm. The motion is too large, too slow, too old to disturb the room. It becomes a kind of silence. Beyond the atmosphere, the solar system continues its measured drift. The moon moves along its pale path. The sun turns in its own fire. Farther away, red stars breathe. Neutron stars keep their faint rhythms, and galaxies carry their arms through wide fields of gravity. Each motion belongs to the same universe, not rushed, not waiting, only continuing. The darkness between them is not empty. It is spacious enough to hold every orbit, every pulse, every slow return of light. On Earth, night gathers softly over water and stone. The magnetic field curves outward into space. The planet turns beneath it, carrying forests, sleeping streets, cloud banks, deserts, and quiet seas toward another dawn that has not yet reached the horizon. Deep below, iron still moves in darkness. High above, particles from the sun pass around the invisible shelter of the field. The whole world rests inside motion. The mind can let the scale grow dim now. Black holes, red giants, radio pulses, spiral galaxies, and the hidden core of Earth all recede into one calm image of a universe turning without sound. The sky remains overhead, the ground remains steady, the night remains wide, and in that width, the old motion of matter continues, slow and patient, carrying everything gently onward through the dark.